Hi, I'm Mrs. Edwards, and today we're going to learn a really powerful rule to differentiate. What we have been doing to this point is we've been finding the derivative using a limit definition. There are also a number of ways to ask the same question, find the derivative. So here are a few different ways that you might see it. F prime of x, y prime, dy dx, d dx. You might even see it written as find the instantaneous rate of change or the slope of the tangent. All of these are equivalent. They all are just asking you to find the derivative. Now, using this limit definition to find the derivative, it might make you feel like this. But fortunately today, when we start these rules for differentiation, we're going to be able to avoid using the limit definition to find the derivative, and it's going to be so quick. Before we jump to the power rule, we are going to find the derivative of f of x one more time using the limit definition. So we want to find f of x plus h and f of x and make a substitution. So f of x plus h just means I go into my function and replace every x in the function with x plus h. So this became x plus h to the fourth power, and f of x was x to the fourth. So I made that substitution. The next thing I have to do is expand x plus h to the fourth power. X plus h times x plus h times x plus h times x plus h. And after we do that, we get this. Okay, I might want to simplify the numerator. That x to the fourth minus x to the fourth, that's gone. Then when finding a limit, you want to substitute the number in. So if I replace every h in this expression with 0, I end up getting 0 over 0, which is an indeterminate form. And then that tells me I should factor, cancel, resubstitute. So in the numerator, there is an h in common to all of the terms. So I factored out that h, allowing me to cancel. This is the expression we have left over. So resubstitute the 0. So we're going to have 4x to the third plus 6x squared times 0 plus 4x times 0 squared plus 0 cubed. And we get the derivative is 4x cubed. Whew, that was a lot of work. All right. Now, what's the meaning of what we found? Remember, a derivative is the slope of the tangent, but this is generic because we have, we didn't say at 2 or at 7, but we can use that to find at a specific value. So I've just made a quick sketch here of what the function f of x looks like, the x to the fourth. Now, if I did use what I found here to evaluate the derivative at 0, right, I substitute 0 into my derivative and I get out 0. And so at x equals 0, that means the slope of the tangent to x to the fourth is 0. Maybe just one more there. If I substitute 2 into the derivative, that's giving me the slope of the tangent to the function f of x at 2. So at 2, the slope of that tangent line is 32. This was a lot of work to get from x to the fourth to 4x cubed. So what we're about to do is we're going to use something called the power rule, and that is going to allow us to get from x to the fourth to 4x cubed without all of that. Whew, victory is ours. To avoid finding the derivative using the limit, we're going to use this power rule. So jot this down before you move on. Once you have learned the power rule, it is going to be really tough for you to go back to finding the derivative using a limit. It's almost going to be this painful memory that you try to forget. But please don't forget how to find the derivative using the definition of a limit, because it will show up on the AP exam and our semester test. All right, but let's check this out. The derivative, d dx, the derivative of x to the n. So this power rule only works when you have something that looks like x to the n. So the derivative of x to the n equals, now the n moves to the front, and then we subtract 1 off the exponent. That shouldn't surprise us that the degree goes down by 1 because we've already graphed several derivative functions. If we had a cubic, then it looked like a parabola. If we had a parabola and then graphed its derivative, it looked like a line, and so on. Let's start with the function that we just spent quite a bit of time finding the derivative using the limit process. If we use the power rule, the exponent 4, there's my 4, it's going to move to the front, and then we're going to subtract 1 off the exponent. So, move that over, 4x, and then subtract 1 off the exponent to the third. What? That was so crazy fast. All right, let's try another one. If I want to use the power rule instead of that limit definition, the 3 moves to the front and we subtract 1 off the exponent. And there's our derivative. Let's try it again. If I find the derivative of f of x, the exponent moves to the front and we subtract 1 off the exponent. So 2x and then to the first power. Now here you don't see the exponent, but we know that the exponent is 1. So if you move the 1 to the front, 1 times 1 is 1, and then subtract 1 off the exponent, that's 0. So we have 1x to the 0. Well, anything to the 0 power equals 1. So we're going to end up with 1 times 1, which is 1. All right, how about that one? Find the derivative of 5. If I find the derivative, I don't see the x, but it's there. It's x to the 0 power. X to the 0 power is 1, and 1 times 5, I'm right back to 5. All right, so when I apply the power rule, I'm going to take the exponent and I'm going to move it to the front. So 0 moves to the front. 0 times 5 is 0. And then if I subtract 1 off the exponent, we would have x to the negative 1, but it doesn't really matter because 0 times anything is 0. So our derivative of f of x is 0. All right, here's another one. Let's say that we have the function f of x equals 2x plus 5, and we want to find the derivative. Oh, I know it's so painful, but let's go ahead and use the limit definition to find that the answer is just 2. Here's my process. All right, now if I want to find f of x plus h, I go into my f function and replace every x with x plus h. So that x right there turns into x plus h. So we're going to have 2 times x plus h plus 5. That will be our f of x plus h. And then minus f of x is minus, and f of x is 2x plus 5. We make sure we put it in parentheses so that we remember to distribute the negative. Okay, I go ahead and simplify there a bit. I have 2x plus 2h plus 5, and I distribute the negative through. I'm going to go ahead and simplify right here without writing a new step. We have this 2x, and that one goes away. 5 and minus 5, that goes away. Now, right now, if I did substitute 0 in for h, I would have 0 over 0, which is an indeterminate form. So then I would cancel the h's to resubstitute, and I get the limit as h approaches 0 of 2, but the limit of a constant is equal to a constant. Whew, that was a lot of work to find 2. All right, here's a picture of f of x. Here is 2x plus 5. It's just a line. And so no matter where I go on this line, what is the slope? Right there at, say, negative 3, f prime of negative 3 is 2. F prime of negative 1 is 2. That's because no matter where I am on this line, the slope is going to be the same as the slope of the line. It's really great to use the power function rule, and you just have something memorized, but you sometimes memorize it and forget what it is that you're finding. So I just wanted to show you a picture here again of f of x is 2x plus 5 and say, well, of course, if you have a line, the slope, no matter what x value you're at, is going to be the same as the slope of the line. Now, if we think of it with the power rule, if I were to use the power rule on 2 to the x, okay, x is to the first power, so the 1 would come to the front. 2 times 1 is 2. X, subtract 1 off the exponent, so 1 minus 1 is 0. So we'd end up with 2x to the 0, but 2x to the 0 is 2. And then the derivative of 5, well, that's like right over here, 5x to the 0 and 5. Those are the same thing. So the 0 comes to the front, and we have 0 times x to the negative 1, which is just 0. Okay, so I could use the power rule twice there, and I get 2. This is also why when we graphed the derivative of 2x plus 5, we just got a horizontal line there at 2, because no matter where we're at, the answer is 2. In the couple examples that we're going to look at right now, the only difference is that there is a leading coefficient, and that leading coefficient is called a constant multiplier. So to use the constant multiplier rule, you just use the power rule but multiply by the constant out front. Okay, so that just amounts to, when that 4 moves to the front, we're going to have 4 times 5, which is 20, subtract 1 off the exponent. So we're going to have 20x to the third. Now, just to change up the notation, because this notation is interchangeable and you're going to see it a lot of different ways. So instead of calling this the derivative of f, like f prime of x, I'm going to use the notation dy dx. F prime of x and dy dx are interchangeable here. We have the derivative with respect to x. Okay, then how about this one? What's the derivative of 2x to the third? Well, we're going to have 6x to the second power. Holy cow, that's so fast. All right, here we go. Exponent moves to the front, negative 16x to the first power. All right, then we have this one. Please don't lose sight of what it is you're finding. It's great if you're thinking, okay, I'm going to move the exponent 1 to the front. 2/3 times 1 is 2/3. Subtract 1 from the exponent. I'm going to have x to the 0, and I end up getting just 2/3. But please, like, it's so much faster in your mind if you're like, okay, I have a line. No matter where I am on the line, the slope is going to be the slope of the line. It's 2/3. Or if your function f of x equaled 7, that just means you have a horizontal line at 7, and the slope anywhere on that line is 0. So just don't forget what you're finding. We would like to continue avoiding using the limit definition of a derivative. But to use the power rule, it has to look like x to a power. Right here, we have a cube root of x. So what we can do is rewrite it so that we see the x to the power. So going from root form to exponential form, I'm going to have x to the power of 1/3. Now that exponent is standing out so that I can move it to the front and subtract 1 off the exponent. Quick reminder of, changing forms there is I call it inside out. The exponent on the inside is 1, and then 3 is on the outside. So this becomes inside out, x to the inside out, x to the 1/3. Okay, so the 1/3 moves to the front, and you subtract 1 off the exponent. So 1/3 x, and then 1/3 minus 1 is negative 2/3. I'd like to simplify it because I don't like those negative exponents. So x to the negative 2/3 is like 1 over x to the positive 2/3. So if you have 1/3 multiplied by 1 over x to the positive 2/3, multiplying fractions, multiply across, we're going to get 1 over 3x to the 2/3. Okay, over here for this one, we have divide by 5. I don't like divide by 5 because I want to see a number x to a power. So we can rewrite dividing by 5 as multiplying by 1/5. So I'm going to rewrite this as 1/5 x to the third power. So if you're dividing by a number, just think of it as multiplying by the reciprocal, and that makes the number x to the power stand out. Okay, now I can use the power rule. So the exponent 3 moves to the front, so I'm going to have 3 times 1/5, which is 3/5, and then subtract 1 off the exponent, so it'll be to the second power. This time I went with y prime for the notation for derivative, so y prime equals 3/5 x to the second power. We're going to go ahead and take this one step further. This is a very, very common problem that you'll see on the AP exam, particularly in the multiple choice section. Find the values of x for which the curve has a horizontal tangent. All right, if you have a horizontal tangent, you've got, some curve, a horizontal tangent. If you have a horizontal tangent, what is that? The slope is 0. So this is really just saying, where is the derivative equal to 0? Because the slope of a tangent line, right, means derivative, and all horizontal lines have a slope of 0. Okay, so we're just kind of translating that, and then now that I know I want to find the derivative where it's 0, that means I better find the derivative of this function and set it equal to 0. We can use the power rule on each of these individual terms, but before I use the power rule, I want to make it look like a number x to a power plus a number x to a power. So I don't like these divide by 3s and divide by 2. So I'm just going to rewrite that as 7/3 x to the third, and then I'm going to have plus 13/2 x squared, and then still the 6x minus 1. Notice x to the third over 1, 7 times x to the third, I'm right back here. 3 times 1, I'm right back here. Okay, so that goes there. All right, so now I'm ready to use my power rule. 3 moves to the front. Now if you move 3 to the front, 7/3 times 3 is just 7. Subtract 1 off the exponent, x to the second. So this will be 7x to the second. So my f prime of x is so far 7x to the second. Now the 2 comes to the front, 13 over 2 times 2. The 2's cancel and I get 13. Subtract 1 from the exponent and I have x. Now the derivative of 6x, absolutely go for it, use your rule. 1 goes to the front, I have 6. Then I have x to the 0, and 6 times x to the 0 is 6. Or you're like 6x, that's like a line. The slope everywhere is the same as the slope of the line. So the derivative of 6x is 6, and then here's a constant, and you know the derivative of every constant. Like, what does y equals -1 look like? It's just a horizontal line at -1. And no matter where you are on that horizontal line, the slope is 0. Okay, so the derivative of -1, the derivative of a constant is 0. If you want to use the power rule, you have to imagine sitting next to -1 is x to the 0 power. So when the 0 power moves to the front, -1 times 0 is 0, x to the -1, and we get 0. All right, so here we have the derivative, and we want it set equal to 0. From here, you should be able to use your skills to evaluate, or to solve for x. You can hit pause for a second if you'd like. You should be able to use the quadratic formula or factor set each piece equal to 0. However you do that, you end up getting that x is -6/7 and x equals -1. We have the answer, we've solved the problem, but I want to go ahead and just draw a picture of what happened so that you understand again what it is that you're finding. Okay, so here's a picture of f of x. I graphed the 7x to the third over 3 plus 13x squared over 2 plus 6x minus 1. Okay, there's that cubic. Now, we just found that the slope of the tangent at -6/7, so right there, and at x equals -1, right there, that the slope of the tangent line is 0. Now, it's not zoomed in. The way it just looks kind of standing a ways back from it, you're like, how is that the slope 0? They kind of both look like they're the same height. Well, what we just did, I'm going to zoom in on that. Okay, if I zoom in there and just like look at it with a magnifying glass, what that part right there actually looks like, that point right there is that one, and that point right there is that one. So if you zoom way in to this, the graph actually is going up, increasing until it gets to this point, then it decreases, and then it increases, and then continues to increase. So see how this guy here, now it's a little more obvious. Yeah, the slope of the tangent there at -1 is 0, and the slope of the tangent there at -6/7 is 0. So we wouldn't be able to tell that by standing back and looking at this graph that we actually had a local maximum and a local minimum. It just kind of looked like it flattened out. All right, but please make sure you put into your notes, if you want to find a horizontal tangent, what you're really doing is finding the x values where the derivative equals 0. Today, you learned the power rule, and that is helping you to avoid this long way of finding a derivative using a limit. Now, if you don't see something that looks like a number x to a power, well then try to force it to look that way by maybe going from root form to exponential form, or if you're dividing by a number, multiply by the reciprocal to get that constant out front. Notation reminders, all of these mean find the derivative. Okay, and then I really want to emphasize one more time, even though I know our focus is the power rule, where here I might say, oh, 2x to the 0 power, move the 0 to the front, and so on. Y equals 2 is a horizontal line. If you have a constant, it means you have a horizontal line, and the slope everywhere is just 0. So the derivative of a constant is always 0. And then if something is linear, no matter where you are on that line, the slope is the same as the slope of the line. It is faster just to understand that you're dealing with a horizontal line or a slanted line there, because finding the derivative is even faster than using the power rule. I really can't help myself. The math jokes, there's so many of them. What is the derivative of a cow? Prime rib. And some sage advice, please don't drink and derive. My husband says, mathematicians, you can dress them up, but you still really can't take them out. Just teasing. If you found even one of these jokes funny, you've probably found your people.